my pleasure to announce a next talk by Juan Pedraza. He will tell us about quantum correction to entanglement entropy after local quenches in AdS3 cross CFT2. Please, 45 minutes.
Okay, thanks a lot for the invitation. So I'm going to talk about quantum corrections to entanglement entropy in holography. So I'm going to start with one slide of a summary of what we did and then the results. So we don't lose focus on the end goal. So we computed, as the title said, we computed the leading 1/n corrections to entanglement entropy after local quench, both in CFT and in the holographic dual. So in CFT, we use conformal symmetry in 2D and large C, large central charge techniques. In holography, we first find the gravity dual to such states, and then we use the FLM formula for computing entanglement entropy. So these are basically the two results that I want you to already take a look at this. So the first one is that, of course, we find that the two computations match. That's already a non-trivial check on of the FLM formula in a dynamical setting. And second, and this was a byproduct of this calculation, we observed that the bulk entanglement entropy follows a page curve, and I will try to explain simple toy model for black hole evaporation. This is based on a very recent paper that appeared last week in collaboration with Cesar Aragon from Stony Brook and Sagar Lokhande from Urbana. Okay, so this is more or less the order of my talk. I'm going to start one slide of motivation. Oops, sorry. So the main motivation that led to this study was trying to understand quantum entanglement of matter fields coupled to dynamical gravity. So this is a very important problem in gravity. For example, for the information paradox, we already had a couple of talks last week on this subject. And in a nutshell, this paradox arises because of the calculation by Hawking that computed the entropy of the Hawking radiation on an evaporating black hole. And he realized that even if the collapsed matter was initially in a pure state, the entropy growed monotonically in time, ending up with a mixed state with finite entropy for the radiation, and that is inconsistent with unitarity. There is, of course, at the moment, it led to a controversy that it took over again last year with this set of works. One of the outcomes of these works is that they explain that the calculation by Hawking, of course, he used a coarse grain entropy in which he assumed that the quantum fields were living on a semi-classical gravity. And so the calculation was of a coarse grain entropy. And they argued that the original calculation didn't include all relevant saddle points. One of the effects of that is that they show that when you include all relevant saddle points, there are in fact one extra piece that competes, and that's what they call the island contribution. Now, what we wanted to do is to try to understand genetic situations where we have matter fields interacting with gravity in a dynamical setting, in a framework that at least we have a control over in the UV. So one of those setups is, of course, given by AdS3. In AdS3, we have many time-dependent situations under control. And we also have a way to relate quantum entanglement in the bulk to quantum entanglement in the dual CFT. That's through the FLM formula. And our idea was to initiate a systematic study of these dynamical cases with the end goal of trying to apply these techniques to a situation where we have a evaporating black hole in the bulk. So the very first example that we tackled was the case of a local quench. A local quench is actually perturbative, so it's very simple in the bulk. Along the way, we learned several lessons, one of which is that we realized that we can, in fact, make contact with the original motivation. And I will try to show you why is this the case. So this will come up at the end of the talk. Okay, so let me start with the CFT story. So we start with a vacuum state, and we perturb it by a local operator, a primary. Once we do that, we evolve the state using the CFT Hamiltonian. Here, a remark here is that if the state is completely localized, then that will include the modes of arbitrary high frequency, and then that would lead to divergences in several observables. So one way to avoid this is to regularize the state. So we add a small imaginary part, this is this alpha, to the time component. And in such a way, this alpha acts as a UV cutoff for modes of high energy. So this is a pictorial representation of this local quench. We excite the vacuum state at some point, and then we let it evolve. For the purposes of the calculation, it's useful to go to Euclidean time, in which case we get this density matrix. These operators now are in the Heisenberg picture instead of the Schrodinger. So I'm assuming that the operators evolve in time. And then I can use Euclidean path integral techniques to tackle this problem. So this is in Euclidean path integral formalism. This is the components of the density matrix. This path integral has open cuts in 0 minus and 0 plus, and this is where I give conditions for the field psi that generate the bra and the k. I also need the reduced density matrix because I want to compute entanglement entropy. So I have to take the partial trace over the complement. That is done by gluing the two cuts in the complement and summing over the field configurations there. So this is the result. And I also need to properly normalize the reduced density matrix. So I have to divide by the trace. The trace is actually, I have to take, this is a partial trace, and then I need to consider the full trace, which is by gluing the two, gluing over the whole cut, both in x, including for all x, essentially. This is the result, and then basically this normalization factor is what I call the C1. The advantage of working on in the path integral formalism is that I can relate the moments of the reduced density matrix as path integrals over a multi-sheeted Riemann surface. This is what people normally do. For example, if I'm interested in computing this moment, that's throw of rho to the n, then I can essentially carry out this calculation as a path integral. Now, instead of with two operators inserted, now I have to insert two n operators in this topologically non-trivial manifold. But that's what later is going to help in the calculation of entanglement. So for that, I have to remind you the formula for entanglement entropy is just the Neumann entropy associated to the reduced density matrix. In practice, the way to compute it is to implement the replica trick. So that's why we need the moments of the reduced density matrix. And then provided I can analytically continue this result for any n in the vicinity of 1 and take this limit, then I can compute entanglement entropy in this way. Now, with these definitions that I had before, it's easy to see that the entanglement splits into two pieces. The last piece is basically a contribution from the vacuum state in the ground state, which for my purposes, I want to subtract. I'm not interested in this part because this is time independent and it includes all UV divergences. So I subtract this piece. I'm only interested in the difference. And it's given by this logarithm, this limit. As you can see, the numerator inside this logarithm is a 2 endpoint function. The denominator is a 2-point function to the n power. So I'm going to exploit the conformal invariance in 2D to map this calculation to a simple setup in which I don't have to carry out the path integral in this complicated Riemann surface, but instead I can map it to a calculation in the complex plane. So in 2D, the conformal maps are one-to-one to these analytic coordinate transformations. And indeed, a map that implements what I just described is the so-called uniformization map. It's given explicitly by these equations. What it does is it maps this manifold that I had to the complex plane. Like with these formulas, you can realize that each shade of the manifold maps to a specific wedge with certain angle. Then the endpoints of the interval, like XL and X right, they map to the origin and to infinity respectively, but infinity along a certain angle fixed by n. And then the last thing that I want you to have in mind is that I still need to compute a 2 endpoint function in this complex plane, but I have only 2 points per wedge, and all of them are related only by a phase. Okay, so how does the entanglement entropy transform under this conformal transformation? So first, this is the formula for the transformation of one operator when I do a conformal transformation. In our case, we have h bar is equal to h because my operator is scalar, it doesn't have any spin. Then what it happens is that this 2 endpoint function in the original manifold, it maps to a 2 endpoint function in the complex plane. These factors in front are just Jacobians that arise by all the products of these derivatives. Plugging this into the original formula, then I can realize, I can split my entanglement entropy as the sum of 2 pieces. One that comes from all the Jacobian terms, and all the second part that comes from the two endpoint functions. So the first piece is completely kinematical. It does not depend on the specific CFT. It only relies on conformal invariance. That's why we call it a universal piece. While the second term, it depends on a 2 endpoint function. And as you know, the higher point functions in CFTs are not universal. So we call this term a dynamical term. So I'm omitting here the details, but this is very easy to compute. The first term, the universal term, you just take a bunch of derivatives to compute these Jacobian factors. You plug them there, and then you get a universal result for any CFT. This is the universal piece. Now for the second term, the term that we call dynamical term, as I said, is not fixed by conformal symmetry, so I need to specify more data. The way that we did it is to consider the limit of a small insertion points, where the 2 points are very close to each other. These are complex coordinates, but this translates to a specific limit in the original variables. And what happens there is that in this limit, then the two endpoint functions, the two end insertion points, they approach to each other in pairs, as is represented in this plot. So what I can do there is to use an OPE expansion pairwise, and I can expand the product of the two as an OPE expansion. Okay, so this one here is the contribution from the identity. This phi is represented all the primary operators, and then of course I have a contribution from all the descendants, and these are the OP coefficients. Next, since I want to compare this calculation to a holographic calculation, then what I need to do is to restrict. We're going to focus on holographic CFTs. That means that I will work with CFTs with large central charge. Then that imposes some constraints on the kinds of OPE coefficients that we have. The one, on one hand, large C implies that for single trace operators, these OPE coefficients are suppressed in 1 over C. This is essentially a result of large C factorization. And then I can use known results for the extra OPE, the OPEs that come from not for single trace operators, but from multiple trace. They can be order 1. And I take the leading term that can appear in this expansion is the one with lowest conformal weight, that is the double trace operator OO. And I just take the OP term. Then what happens is that taking into account the leading and the subleading contribution, then I can represent the two endpoint function as a product of OP expansions. Here I'm keeping only the first 2 terms. The first one is the one that appears where all the OPs are replaced by the identity. And the second is when 2 of the OPs are replaced by this operator. The case where only one is replaced, it doesn't appear because then it amounts to compute a 1-point function of this operator that is local. And in the vacuum, that expectation value is 0. So this is why this is the first non-trivial contribution. Then I can carry out the sum, and then again, I'm omitting the details, but this is the end result. And again, since I use the OPE, this is only valid when these 2 points are in the limit where these 2 points are nearly coincident. Okay. So both this and the universal term, I have given the results in terms of these complex coordinates. Then the last step is to analytically continue this back to real time, but that's very easy. Okay, so I'm gonna move to the holographic part. Is there any question for now for this part? Okay. So let me now move to the holographic description. So in order to understand the dual, this concept that's developed in this paper a couple of years back. What they proposed is that the holographic dual for a local quench was given by the back reaction of one particle in empty AdS. So going to Poincaré AdS, they have this combined action for just pure gravity plus a particle. They can, first off, they can assume that the particle does not back react on the geometry. And you can read off, for example, the geodesic that it should follow. So it's given by this, this parabola. So alpha here is the distance of closest approach to the AdS boundary, and it evolves in time given by, like, the time evolution is given by this formula. For my purposes, I'm gonna just take this solution as starting from time equals 0, and then consider the evolution starting from time equals 0. Then next step is that you need to consider the back reaction. So this particle has a stress energy tensor in the bulk, and of course it sources a non-trivial gravitational field. Solving this problem is in fact difficult, but what they realized is that there is actually a clever trick to solve this problem. The trick is that you can start in global AdS, having the CFT on a circle where you know that the back reacted solution looks like a conical deficit. Once you have you realize that that is the back reacted solution that you're looking for, then you can specialize to a Poincaré wedge. So here I'm writing explicitly embedding coordinates, and then AdS coordinates in both coordinates, in global and in Poincaré coordinates. There is a small problem here, that is that if I just implement these transformations as they are here, then my R equals 0 geodesic maps to this geodesic, which indeed looks like the geodesic that I wanted, but the approach, the distance of minimal approach to the boundary will be given by L. It's not going to be arbitrary. So one way to fix it is by adding an extra boost in the embedding space. So this particular boost is along the Tx direction that gives rise to this e to the beta factor, that's a boost factor. And by doing so, then you can realize that the R0 geodesic now maps to this geodesic in the Poincaré frame. So this is indeed what you wanted. And that specializing then to this Poincaré wedge is what allows you to do calculations in the quench state. Now, this original model is a little bit simple for what we want. First, because we actually want to compute bulk entanglement entropy, and that requires the knowledge of the wave function of the one particle state. Second is because this approximation, in which I replace the one particle state by just a classical particle, is only valid for operators of large conformal dimension. While at least if I want to compare with the CFT results, I want arbitrary delta, not necessarily large. So the way to go forward is to consider instead this bulk action. This is a gravity coupled to a scalar field, and considering a one particle state in this scalar theory. So what I'm going to do here is a quantum field theory coupled to gravity. And the state that I'm interested in is a one particle state, actually the state with the lowest energy, that is basically the vacuum, and then this A00 is the creation operator of with lowest quantum numbers. Now, fortunately, this problem was already solved in global AdS a couple of years back. So I'm gonna just take their results here. First, what you can do is to compute the stress energy tensor in the bulk. That is but by that, I mean the stress tensor in this one particle state. So these are the results taken from this paper. And then once you have that expectation value, then you can use the semi-classical Einstein equation to solve for the back-reacted geometry. So that also was solved in that paper. This is the result at the leading order in G Newton. And indeed, this looks like a conical defect for large delta, but in fact, this is valid for small delta, right? Because I want, this is my expansion parameter is G Newton delta over L. So, and I want that to be small. So this is how the back-reacted state looks like in global. I can then implement the coordinate transformations that Takayagi and company explained in their paper, but now applied to this global metric. If I do that, then I get a metric in Poincare patch that represents my quench state. Okay, so this results in a very long metric that I'm not going to write down, but with that I can, for example, compute several observables. One of them that is going to be useful later is the expectation value of the stress tensor. For that, I need to expand my metric. First, I need to go to the Pfefferman-Graham gauge, in which the DC component has no corrections. It's only one, it's fixed, and I expand my other components. And from this expansion, I can read off my expectation value of the stress tensor as the normalizable mode, right? So this is what I get as a result. These are some plots of the energy density, and this P is the momentum density, that is the off-diagonal term. You can explicitly check that this satisfy all the properties that you want, like it is conserved and the trace is 0. Okay. Any questions so far? Okay. Okay, so now that we have the bulk dual, what we want to compute is the entanglement entropy, and up to.
Sorry, Juan, may I ask a short question about stress energy tensor?
Yeah.
Is this stress energy tensor coincides with local quench stress energy tensor, right?
Yeah.
I mean,
correct.
And but it works for arbitrary delta, right?
Yeah. Yeah. So well,
you consider. I mean, you consider perturbative contributions for a scalar field, one particle state, right? But you get the exact local quench stress energy tensor, right?
So this bulk calculation is valid for small delta, small, like by small I mean smaller than C, but it's otherwise valid at arbitrarily, like, yeah.
Okay.
So no correction of higher order on delta?
Actually, I mean, you can think that it might be corrections, but for example, if you compare this to the one that Takayanagi and company computed, that's starting from the conical deficit metric, then you actually get the exact same form for the stress tensor. So that suggests that at least this is the right one for small delta or for very large.
Mm-hmm. Okay, thank you.
So the final aspect of the calculation is to compute the entanglement entropy. So at the order that I want, I need not only the area term, but the entanglement of bulk fields. So let me first describe how the area term is affected. So since I'm considering the metric up to linear order in G Newton, then the calculation simplifies drastically. In that case, you can see that the change of the area is given by this formula, this trace formula here. But the nice thing is that all these quantities are evaluated using the ground state embeddings. That means that these embedding functions are only the ones in AdS, and that's enough for doing this calculation at the leading order. Okay, the rest of this calculation is very simple. It's just plugging the embedding functions of vacuum AdS and doing this integral. This is the outcome of that calculation. So I have written down two cases. One case is for center intervals, and by center I mean when I have my interval exactly where I insert my local operator. This is the full result in that case, that I can get a closed form. And one observation that I can make at this point is that the first it has two terms. One, this arc cosine, and the second one, this hypergeometric function. But the observation is that this first piece coincides what we obtained in the CFT, and that we call the universal piece. This is for center intervals. For non-centered, I cannot get completely closed expression like this, but I can get it for integer delta, but it's quite long, that I didn't write it here. But what I wanted to point out is the general structure of the result. So in general, I can expand my result as two series. The first one comes in powers of r. R is the half length of the interval. The first series comes powers from the r squared and sublime terms that some even number. The second series has a leading term of order r to the 2 delta and has corrections of this form. The observation here, and what might seem a little bit puzzling at this point, is that from the CFT, we did not find this kind of corrections. So the only possibility is that this second term should cancel with the quantum corrections. So that's what I want to see next. Before that, let me just make a small parenthesis. The small parenthesis is to analyze what happened when you have a perturbative state. So as you know, if the state in the CFT is small, is perturbatively close to a reference state, and in this case is the vacuum, then what happens is that the entanglement should satisfy the first law. What happened in our case is that the local quenches are not in general perturbatively close to the vacuum. In fact, this one particle state in the bulk is orthogonal to the vacuum state. But we can ask if there is an additional expansion parameter such that not the full density matrix, but the reduced density matrix is close to that in the vacuum. So the answer is yes, and the small expansion parameter can be given by the size of the region. So I have plotted here 3 cases in which this might be true, all of them involving the size of the region being small. If that is the case, then I can assume that the stress tensor is approximately constant, and I can perform this integral. I can do it, and then I can extract, in fact, the leading term for small intervals. Now, I said that local quenches are not perturbably close to the vacuum, but that I meant that there are higher order corrections that can appear even at the same order. But still, the first law should give me the full result at order delta rho. Then I can plug the stress energy tensor, and what I get is that the result of this calculation gives me exactly the universal term. So I just mentioned this because it's going to be important in the next slide. Okay, next, I want to consider the bulk entanglement entropy corrections. For that, I split the calculation in two parts. First, I consider corrections that are linear in the density matrix. And second, I can consider higher order corrections. So at a linear order, I can use the first law in the bulk. In the bulk, I know the bulk modular Hamiltonian associated to this codimension 1 surface in the bulk. And this killing vector here, instead of being the killing vector in the CFT, is the killing vector in the bulk that generates this surface. The rest of the ingredients are the induced metric on this Cauchy slice. This is a normal vector that if I picked a Cauchy slice at constant t, then it will be a normal vector pointing in the time direction. And then this is the bulk stress tensor. Just carrying out this calculation, what you can see is that order by order, you recover all the terms that needed to cancel precisely the second series in the area term. And in fact, this is not surprising because this is what we expect from the exact relation between CFT and bulk modular Hamiltonians. So this cancellation is not surprising. It's indeed what it was expected. So there are two more aspects of the calculation. The one is doing this calculation at higher orders in delta rho, and the second is the interpretation. So I'm gonna first talk about the interpretation. If I plot the result of the bulk entanglement entropy, I get plots that look like this. This is what happens for center intervals, and the plot in the right is what happens for non-center intervals. In the next slide, I'm gonna argue that this plot can be interpreted as a page curve. And in fact, is what you expect. So you expect that it grows, initially it grows in time, and then it decreases again to 0 as t evolves. Okay, so for this interpretation, there are two aspects to understand this interpretation. So the first one is that if you go to coordinates adapted to this entanglement wedge in the bulk, this is the so-called Cassini-Huerta-Myers map, then in fact, this entanglement wedge looks like what is called as an hyperbolic black hole, right? So what we are computing as viewed from these Ringler coordinates is the entanglement entropy of bulk fields of the exterior of this hyperbolic black hole. Second, the second point for this understanding this analogy is that if you see this entanglement wedge as seen from the global picture, from global coordinates, then what you realize is that at different time slices, what you have is an entanglement wedge of different sizes. So here in the Poincaré, what I'm interested is in fixing the interval and doing this calculation at different Poincaré times. But in global, that means that I'm varying the size of my entanglement wedge. In fact, once you do this map between Poincaré and global, you realize that the size, it decreases monotonically in time. But that it means that this hyperbolic black hole is in fact decreasing in time, in Poincaré time. So that's why this calculation is very analogous to computing the entropy of the Hawking radiation in an evaporating black hole geometry. Any questions about that? Okay.
Sorry, can I ask a small question?
Yeah.
Can you explain a little bit, repeat maybe, which exactly black hole do you mean? Does this result reproduce the page curve for the two-dimensional black hole, which is due to the AdS3 Almeri Moldasian Mahajan, or some other black hole?
Yeah, so this black hole is in fact the interior of the entanglement wedge. So this is a bulk black hole. So if you go to these coordinates adapted to the wedge, what you realize that the metric looks like, looks like precisely like this form, which is nothing but a hyperbolic black hole. In 3 dimensions, this is a planar BTC black hole.
Okay.
Right. So this is how it looks like for a Rindler Rindler coordinates adapted to the wedge.
Okay.
Okay. So this is explained in this paper of Cassini, Huerta, and Myers. But so that's one part of the interpretation. The second part is that, as seen from the global picture, the calculation that I'm doing is actually a bulk entanglement for an entanglement wedge that is decreasing in size. That means that this black hole, this hyperbolic black hole, is in fact decreasing in size.
Right.
Okay, so one thing that is nice of this picture is that we can understand the behavior of the page curve as following completely from the purity of the state. So one way to see it is that if the state is pure, then you know that the entanglement entropy of a given subregion is equal to the entanglement entropy of the complement. So this is one way to see, to derive it, is from the Araki-Lieb inequality that is given here. And if the state is pure, then this is bounded by 0, which means that these two quantities are equivalent. The second ingredient is that entanglement entropy should be monotonic with size. So if you are in flat space and you compute entanglement entropy as a function of the length, it should always be increasing. And in a compact space, this should still be true up to when the angle is, like in this case, is half of the size, right? The reason is that due to the first point, then entanglement entropy for regions larger than pi are actually equivalent to entanglement entropy of 2 pi minus the angle.
Sorry, can I ask another question right away? Isn't the whole point of the page curve is to actually verify that the state is pure?
No. Here, the whole point that I want to make here is that the behavior of this curve, first increasing and then decreasing, can be explained from the purity of the state, at least in this model. Okay, so let me just so if you combine these 2 points, and then if you replace the entanglement for time in this plot here, I'm drawing the RT surface at 3 different times. One at a time less than the page curve, less than the page time. The second is at time equals the page time, and then at time that is larger than the page time. So if I now replace my entanglement wedge for the first case, for that of the complement, then what I see is that this setup is completely equivalent of having an entanglement wedge that first grows in time, grows up to the page time, and then decreases. Okay, this combined with the second point, then that explains the growing and then decrease of the page curve. But again, this follows entirely from the first property that is only true for pure states. Okay. So this is my last slide. My last slide is just showing the calculation at next order in delta rho. Here, we can only do it for in the limit of small intervals, while the result at linear order was valid for any size. And I'm just gonna flash this. This is in order to go to higher order, then we need to implement the replica trick in the bulk. And by doing so, I can isolate the terms that are quadratic delta rho. This is the result. This is the formula, but the last piece, in order to evaluate this trace, is convenient to work in the coordinates adapted to the Ringler wedge. For that, you need to map the field expansions in the two frames, and in particular, you need to compute the Bogoliubov coefficients for that transformation. The computation is a little bit technical, but once you do that and you express this in terms of the Bogoliubov coefficients, you can extract. We can do that asymptotically in the limit of a small r, but just by doing that, we can extract the leading term, which indeed matches the first term that comes from the OPE. Then these are my conclusions. So with that last check, we have indeed verified that the two results match. And the second point is what I explained before, is that this calculation can be seen as a simple model of unitary black hole evaporation, and that in our model, we can clearly explain the behavior of the page curve as a result of the purity of the state. And that's the end. Thanks.
Okay, thank you very much. Well, any questions, please? I guess people are a little tired after 3 hours non-stop seminar. Okay. Dima, Misha, do you have some questions?
I think Pavel has a question.
Please.
Is it possible to generalize these calculations to the higher dimensional case?
From the bulk perspective, I think yes. The difficulty in the CFT is that we use this conformal mapping that relies on the properties of conformal invariance in 2D. But from the bulk perspective, I think is very easy to generalize.
Thank you.
Maybe I have a
question.
Yeah.
So you had this regulator alpha to spread out the state a little bit. Do you know what happens when alpha progressively becomes larger and larger?
Yeah. So in fact, these plots that I showed here are for small alpha. Right. And what happens is that if you take alpha to be large, then the particle will be always outside of the entanglement wedge.
I see.
And then I will only be able to capture the last part of this evolution, the decrease, because I have identified the page time as the time at which my particle crosses the entanglement, exits the entanglement wedge.
But in some sense, I mean, getting larger and larger is sort of approximating more and more a global quench.
Yes. So this alpha kind of measures the support of the local perturbation.
Right.
And if alpha is large, then it will be supported over a large region.
Thank you.
More questions, please?
What would be the dual of, if you consider not a one particle state for a scalar field, but for example, for a vector field or for a graviton, one graviton state that perturbs? Can you calculate, does this make sense? I mean, for example, one graviton state that creates something like conical defect perturbatively?
Yeah, I think it's possible. Like, in fact, in the paper, we wrote it as an outlook to look at those cases.
Oh.
Please, any questions? If not, let's thank Juan for interesting talk. Thank you very much.